So today I'm going to present this paper, Neural Motifs, Scene Graph Parsing with Global Context from CVPR 2018. This is the outline I'm going to take today. So from task and do some analysis of the scene graph and the model architecture, then follow the sample experiment and analysis and the summary. So first, let's define what is the scene graph. So scene graph basically is from the real world image. Then from this image, we can have three important parts. So the first is the bounding box. So the bounding box gives us the objects where we are interested in. So the objects, like in this image, there are human, there are motorcycle, and the human are doing something with the interaction between the objects. So the second one gives the objects. So within each bounding box, there is the class assigned to each object. Then the last part is the relations between these objects. So for example, the woman is riding the motorcycle. So each relationship contains the start node and end node and the relationship label. So it's a directed graph. So why we want this kind of scene graph? So for example, before we just have the image like this way, after we have the scene graph, we can have a structured understanding of this kind of image. So after we got the structure of the semantic context of the image, so it's helpful when we do other semantic analysis, like doing the image captioning and for example, the question and answer based on the image. And also it's helpful for the computer vision system. So before we do the model, we want to do some analysis of the scene graph. So first we talk about the data. So this is the visual genome dataset. So it's annotated scene graph data from the Microsoft Cocoa. So consisting of over 1M instance of objects and more than 600K relations. So when we're building the model, there are two important questions we want to answer. So how different the types of the relations correlated with different objects. So that means the different objects and the different relations, they have some underlying relation with each other. And then the second one is how higher order graph structure reoccur over different scenes. So like within one scene graph, there may be some repeated pattern of the graph structure. So that's also helpful when we're building the scene graph. So first, within the data set, we use some hyperclass. So for example, there are a lot of objects in the Microsoft Cocoa data set. So we have some hyperclass of the objects like person, animal, and parts. And for the relationships, we divide them into three main classes. So one thing is about the geometric, another is the possessive, and the last one is the symmetric. So there are some hyperclass of all the data we have. So we also draw the graph between different relation pairs. So example, so this is the begin node, the head node, and this is the tail node, and the relations are annotated with different color. So here, we can see the clothes and the parts are mostly linked by the possessive relations, which makes sense, like the clothes and parts belong to something of the head object. And for example, the furniture and the building are most linked by the geometric relations. And we can see almost all the semantic relations are conducted by the person. So like the semantic like reading, eating, so something give meaningful semantic means, so are contact by person. So that means when we build the model, the class of the object are important. So then let's go to, so this is give us some prior sense of how the object and the relations are linked together. Then we want to know how the object and the relation give us information when we have one component of the relation pair. So for example, if we given the head and the tail class, when we define the edge label, so it's very likely like if we have this kind of information, then the edge is very easy to predict. So this is the likelihood of guessing label when we give other components of these relations. So this is very also very important. So like if we give the object label and it's already highly predictive of the age, but it's not vice versa. So this all of this tells like there is a global context within all this of all kind of scene graph. Then within one graph, scene graph, there's some repeated pattern of the motif. So when we talk about motif, it's like object relation and object pair. The combination of that motif that repeat appear in the scene. So in the image, like we calculate, like there are a lot of repeated pattern. More than 50 of the image in the data set have at least two lengths of the motif. So this is all about the global thing. So like for example, when we take a look at the first the leaf of the tree, so we can imagine there is a picture of trees, so there are a repeated pattern of the leaf and tree. So for example, in the third one, so there is elephant has head, elephant has leg. So here the motif is the elephant has. So this is from the structure of the image. So then let's go to the model architecture. So this is the whole model of the scene graph. So the key challenge here is to not only predict the object and the relationship, but also compose with the global context. So all we do, all the analysis before, is tell us how the global information is important when we do all this kind of scene graph. So here's the whole model architecture is decomposed into three parts. So first is in the right side, so about the bounding box detection. Then we have, after we got the bounding box, we have the object context. Then we have the final edge context, which predicts the relation. So first is the bounding box. So this is for the very so this is using the faster RCN with VGG backbone. So it's a natural backbone for the bounding box section. So this is like kind of pre-processed. So people do this, and we have the bounding box. Then we propose the bounding box. We have the feature vector of F within each bounding box, and we have a predictor vector to give the potential class of this bounding box. But this only contains the local information. It's not considering the whole global image. Then this all kinds of this information, all the bounding box are linearized, then sent into the second part, which is the object context. So they also use a different way to linearize the to organize how the order sending the bounding box into the next stage, the object context. So the feature we get from the bounding box is sent into a bidirectional LSTM, which encode the global information. So each class is not only related to itself, but also gives the information to other class. So here it's like we use a bi-LSTM to encode the information from each bounding box. And here there are some some hidden parameters we use. Then we can send it to the next stage of the edge prediction. And using this kind of bi-LSTM, then we can do the prediction of the object in this context, in this stage. So this stage gives us, after we have passing the LSTM, we use another one directional LSTM to predict the objects. And the bidirectional LSTM is used to encode the information. So this part get the global information and the local information. Then in the last part is using the encoded information in the object context to train another LSTM, bidirectional LSTM. So here we have the input information of the object context, and we also use the predicted object label, and we put all of information into the bidirectional LSTM. This is used to predict the edge context. And then after we get the encoded information, we combine them with the feature from the bounding box, and together, so it's like one pair to another. So one by one pair, we predict the edge between them. So if they have connection with each other, we predict the edge. So like the dog has hair, or if there is nothing interaction between the objects, then we predict it's a background. So this is the whole structure of the Motif model. So why use this? So actually there's a lot of LSTM bi-direction. So I think this is related to the previous analysis, like the global information is important. So when we're doing the prediction, we need to consider the previous one, how the object is predicted, then we use that kind of information.
So how do they decide the order of the bounding box?
Yeah, so they use different kinds of order. So in the results, they do some different experiments. So for example, they order by the location, or they order by the size, or they order from left to right, and actually all the different orders seems like the final result almost the same. So they say that order doesn't matter actually. So this robust for the order, so actually it's okay.
If order doesn't matter, why do you do that?
That's like
proximity is the matters.
So after they have the model, they do some experiment and analysis. So before that, they give some new frequency baseline. So the first one is like the. So first one is called the frequency baseline. So actually, this one just look at the empirical distribution over the relationship between the objects. So that means this baseline just looking at the data in the training set and the distribution, the empirical distribution, but not use the image information. And the second one is based on the frequency baseline that requires the two objects have some intersection region. So these two baseline, the proposed build based on the analysis before. So let's see the result here. So first, okay. So let's see. First is let's compare the frequent. Here, the frequent and the message passing. So this is the baseline paper. Actually, without the image information, the new baselines already outperform the previous paper. So that means the empirical distribution is very important. So without the image information, we already can give some very good prediction of the label and the scene graph. And then based on the baseline, we have the motif net with non-context. That means we only put the local information, the image information into the model, but not the global one. So that also gives up, the result is better than the frequency overlap model. So that means the image information also help us to generate the better scene graph. So this comparison means like the image information is good, so it helps us understand. Then let's compare with the non-context and the motif left-right. So the left-right is just the whole model. So the whole model takes the global context into the motif network. So this also improves. So this left to right is get the best result. So that means the global context is very important. So when we considering the object and the relationship, we also need not only just focus on this kind of pair of object, and we also need to consider the whole thing. So the global image, the other relation and the object also plays an important role when we predict this kind of relation. So here, the results show the baseline is strong. So this is a new strong baseline. Then there is a signal in the vision feature for the edge prediction. Then incorporating the context is also important. And for the last, so this is talking about how we order the bounding box information. So actually the result seems quite the same. The difference is small. So that suggests like the motif net is robust of the ordering. Then they also do some experiment and analysis. So here's like okay, I'm not sure. So the green one is the brown shoes, and the yellow and the red one is something. So sometimes they show in the brown shoes, and the green one is something the predict but not show in the brown shoes. So the error most there are two kinds of common failure. So one thing is they talk about the predict ambiguity. So like the people wearing and people wears. So that's different according to the brown shoes. Actually, I think that's reasonable enough. Like people wearing and people wears, we can think they are the same prediction. And another thing is the failure comes from the detector failure. So for example, in this image, because the object detection fails to get the house in the image. So all the object and the relation relate to that house is detective failure. So that's another way we can improve our scene graph model. So this failure comes from the object detecting. So the summary is like okay. The motifs are prevent, and it's important to enhance the model. So and second is we introduced a strong baseline. So just look at the empirical distribution of the model, the data in the training set. We are already outperform some baseline before. And the last one is we give a new model, Motif net, to capturing the high order structure. That means the global context and in the scene graph. And it's also improved based on the baseline. So this some this is the author bit. Okay. Okay, this is also give some. Okay, so this is also give some example. So like here is this is the ground truth. This is the motif network they predict. So actually they predict a lot more than the ground truth. And I take a look, so it makes sense. So it's they give the prediction and like the house has window shades, so like they even detect some small part of the image, and the relation and the object is makes sense, so kind of correct. And they compare with the ground truth, so the result is quite good, I think. So okay, any questions?
There's a lot of questions. Any questions?
So before they do the SDM, right?
Mm.
They need to project all the bounding box to the same embedding. How do they do that?
To the same embedding?
Yeah. So
So-
after this one,
Mm.
they have the LTM,
Yeah.
SDM,
Yeah.
which takes the input is the bounding box.
I think they resize the feature space.
They decide.
Yeah, so like fix the feature space from the bounding box.
So if the bounding box too small, and they
Yeah, yeah,
Scale.
yeah. So they use the same feature space.
Any more questions?
So the labels are given by people, right? There's someone that actually annotates all these things.
Yes. So the
Including
ground
the-
truth, I think it's labeled by people. So in the data set, they already give bounding box, label, object, class.
Object class, how about the relationship, the
They're
attribute?
also given.
So then the problem essentially is arriving at the labels
So,
as
so
well as the relationships.
actually, they do three different kinds of experiment. So one thing is just the scene graph detection. So that means you give the road image. So you generate all the things, the box, the object, and the relation.
So then when you say recall what?
Recall like they do the. So there's a bounding box. Then in the you generate. Then there's a bounding box in the data they give. So they compare whether there's some overlap more than how many percentage. Then they say it's the same bounding box kind of.
Okay. But that's just a bounding box. How about
Yeah.
the labels?
Labels, you mean the class label?
So it's here the scene graph detection, scene graph classification.
Mm.
So the detection is the bounding box. Classification is the labels.
No.
The
So
predicate is the relationship.
the scene graph detection is everything.
Everything.
So the scene graph classification is like you give a bounding box and the object, you predict the relation.
Predict the relation.
Relation.
How about the last one? Predicate classification.
Oh, that one is the predict classification. One of these is given the bounding box, you predict the object and the relation. So there are
That's the
three.
second one, right?
Yeah, let me check. Yeah. So one. So the scene graph detection is for the whole thing. So you just
Okay.
yeah.
But
Mm,
at least when we do recall of what? That means everything must be correct.
Everything.
If I may get a bounding box.
I think is add them together.
The final one is the subnet function. A subnet function gives us the probability of the labels, and divided the correct label gets
Right. But the bounding box may not be correct.
I think maybe take the average. I think.
So I may get the bounding box just a small overlap, but I may get the label right.
But I think that if the bounding box is like the overlap is small, so they say it's not
It's
the
not
correct.
counted.
Yeah, so it's not counted. I think at least you need to have the bounding box correct. Then we go to the next stage. So predict whether the object is correct.
Okay, but there's no predicate.
Yeah, I think they take some average of the all the box the relation together.
You need more time. Okay. Okay, so you save the questions for later. Now we have the reviewer.
So do we thank the speaker?
Yes, please.